In the previous lectures, we were solving the problem of the heat conduction in a composite. Okay. Material of thermal conductivity Km, which has spherical particles inclusions in it with thermal conductivity Kp, okay, of height h say, of height L say, across which we apply a temperature difference. Okay. And we wanted to find out an expression for the average flux. Q average is equal to minus K effective delta T by L, where K effective is the effective thermal conductivity. And we were solving this in a dilute limit where the temperature field around one particle does not affect the temperature disturbance due to one particle does not affect the field around another particle. So, each particle can be considered to be a sphere placed in a matrix in which the temperature variation is a linear function of z far from the particle. Okay. So, each particle can be considered to be in a sphere in a particle of conductivity Kp placed in a matrix which has a linear temperature gradient far from the particle of the form T is equal to T prime times Z, where Z is the axis along the direction of variation of temperature, okay, where Z is the axis along the direction of variation of temperature. And we had analyzed this in a spherical coordinate system. Okay, where r is the distance from the origin and theta is the angle made by the radius vector with respect to the plus z axis. Okay. So, theta varies from 0 to pi and the surface of the particle is at r equals r, okay, where r is the radius of the particle. Okay. And we were trying to solve the heat conduction equations del square Tp equals 0 and del square Tm is equal to 0 with boundary conditions at r is equal to r, Tp is equal to Tm, continuity of temperature and Kp into partial Tp by partial r is equal to Km. Okay, so, those were the conditions. This is a problem that is symmetric around the z axis. So, for a given r and theta, if you vary the phi coordinate, the meridional coordinate around the z axis, there is no variation in temperature. Okay. And therefore, the equation for the temperature field, the Laplace equation for the temperature field was written as 1 by r square d by dr of r square partial t by partial r plus 1 by r sin theta And if you recall, we had used separation of variables t is equal to some function of r times g of theta, okay, and substituted that into the equation and multiplied by r square divided by f times g to get 1 over f d by dr of r square df by dr plus 1 over sin theta equals 0. So, those were the equations. Now, the first term on the left is only a function of r, the second term on the left is only a function of theta, both have to be equal to a constant, and we saw that the series solution for G, which can be reduced to a Legendre equation of the form 1 minus psi square d square G by d psi square plus alpha n into G is equal to 0, where psi is equal to cos theta. Okay, just a transformation of variables. You substitute psi is equal to cos theta and then put it into the equation and solve it. This equation has finite solutions which do not diverge or go to infinity at psi is equal to plus or minus 1, only if this alpha n is equal to n into n plus 1, where n is an integer, okay, where n is an integer. Okay. And the solutions for this are G is equal to Pn of cos theta, okay, where Pn is a polynomial of which has maximum power n. Okay, it's a polynomial series in which is truncated at order n. Okay. And you substitute that same eigenfunction, and f is equal to a r power n plus b by r power n plus 1. Okay. So, my solutions for the temperature field in the particle and the matrix, okay, were both of the form sigma n is equal to 0 to infinity of a n r power n plus b n by r power n plus 1 p n of cos theta. Okay. For the particles I will put a superscript p, and for the matrix I will put a superscript m. And these Pn of cos theta satisfy orthogonality relations, that is integral 0 to pi sin theta d theta. Okay, is equal to 2 delta n m by 2n plus 1. That is, these integrals are non-zero only when n is equal to m. Okay. So, these were the equations, the boundary conditions. Okay. At r is equal to r, okay, the temperature of the particle is equal to the temperature of the matrix, the fluxes are equal, Kp partial Tp by partial r is equal to the fluxes are equal. Okay, good. And as r goes to infinity, okay, the matrix temperature is equal to T prime z is equal to T prime r cos theta. And if you recall, I had written down the first few solutions for the Legendre polynomials for you earlier. Okay. So, these were the first few solutions. Okay. P0 is equal to 1, P1 is equal to psi, P2 is equal to 3 psi square minus 1 by 2, etc. Okay. So, these were the first few Legendre polynomials. Okay. Therefore, this can also be written as T prime r times P1 of cos theta, okay, because P1 of cos theta is equal to cos theta itself. P0 is 1, P1 is cos theta, okay, polynomial of order 1. P2 is 3 cos square theta minus 1 by 2, etc. Okay, so, okay. Now I have to find these coefficients AP n, BP n, and similarly in the matrix to satisfy these boundary conditions. Note that all the Legendre polynomials are all orthogonal to each other. Okay. Therefore, if I were to do it in the similar manner as I had done it for Cartesian coordinate system, I would take Pn of cos theta and multiply it by some other Pj of cos theta, and the integral would be non-zero only if j is equal to n. Okay. I do that for the temperature fields and I do that for the boundary conditions. Okay. You can see that the forcing for the boundary conditions is proportional to P1. Okay. The forcing for the boundary condition is proportional to P1. Okay. If I expand out the boundary conditions in a polynomial in an expansion in Legendre polynomials, if I expand out the boundary conditions in an expansion in Legendre polynomials, then the contribution to the boundary condition at infinity is only for P1. Okay. The coefficients for all others P0, P2, etc. are all 0. Okay. If I expand out the boundary condition, then the coefficients for P0, P2, etc. are all 0. Okay. That means that for P0, P2, P3, etc., that component of the temperature field is 0 as r goes to infinity. Okay. And the temperatures have to be equal at the surface, the gradients have to be equal at the surface. Since the forcing for P0, P2, etc. as r goes to infinity is 0 for all Legendre polynomials except for P1. Okay. If I set the coefficients to be 0 throughout the domain, that will satisfy all the conditions. It will satisfy the equation because the equation is del square t is equal to 0. If I set the coefficient of all the Legendre polynomials except for P1 to be equal to 0, it will satisfy the equations. It will satisfy the boundary conditions because they are homogeneous. These just relate the coefficients in the matrix and the particle. So, it will satisfy these boundary conditions, and it will satisfy the condition at infinity, because at infinity there is no contribution to the boundary condition proportional to P0 or P2 or P3 or and so on. There is only one contribution as r goes to infinity proportional to P1. Okay. And because of that, all the coefficients in this matrix except for P1, okay, for all n not equal to 1, okay, are all equal to 0, okay, because there is no forcing at infinity and the coefficients are related at the surface. Therefore, setting those coefficients to 0 identically satisfies the conditions at the surface as well as the conditions at infinity as well as the equations. And therefore, since this is a linear equation, if you find one solution, you are guaranteed that it is unique. Therefore, there is no contribution to the temperature field proportional to the Legendre polynomials P0, P2, P3, etc., because there is no forcing for those Legendre polynomials. The only forcing is for P1. Okay. So, therefore, I can just write these solutions for the temperatures in terms of P1 alone, okay, because there is no forcing for any of the others. Okay. So, therefore, I can just remove these summations here, okay, and just set n is equal to 1. okay, just setting n is equal to 1. Okay. So, this is just equal to 1. Okay. So, this is the only term that survives because there is no forcing for any of the other Legendre polynomials, and all of those Legendre polynomials are all orthogonal to each other. Okay. So, for P2 for example, if I expand out the equation and the boundary conditions, the boundary condition at infinity is 0. The boundary condition at the surface, the coefficients are related to each other. Okay. There is no inhomogeneity in these boundary conditions, and the equation is satisfied if the coefficients are 0. Okay. The only case where the boundary condition is not satisfied is for the coefficient of P1, because I know that for the coefficient of P1 the temperature field is non-zero at infinity. Okay. So, therefore, I can set all coefficients equal to 0 except for the coefficients for n is equal to 1 for the Legendre polynomials. Okay. So, once I have done that, I have to apply the boundary conditions at the surface. Okay. Within the particle, the temperature has to be finite. Okay. Within the particle, the temperature has to be finite. Okay. You can see that this term goes to infinity within the particle. Okay. This term goes to infinity at r is equal to 0, which is within the particle. There is no physical boundary there, and therefore, the temperature cannot go to infinity at r is equal to 0. So, this coefficient Bp has to be set equal to 0, n is equal to 1. In the matrix, as r goes to infinity, okay, in the matrix as r goes to infinity, right, the coefficient proportional to B1m goes to 0. The coefficient proportional to A1m increases proportional to r. Okay. And you have the condition that the temperature has to be equal to T prime r times P1 of cos theta as r goes to infinity. And that equation will be satisfied only if A1m is equal to T prime. Okay. Only if A1m is equal to T prime will that condition be satisfied. Okay. And then we are left with two coefficients which have to be evaluated from the boundary conditions at the surface. Okay. We are left with two more coefficients that have to be evaluated from the boundary conditions at the surface. So, let me rewrite the temperature fields. Okay. In the particle, the temperature field is equal to A1P r times P1 of cos theta. In the matrix, the temperature field is equal to T prime r plus V1m by r square times P1 of cos theta. Okay. This now satisfies the equation as well as the boundary condition at infinity. Okay. This satisfies the equation as well as the boundary condition at infinity. Okay. And now these A1P and B1m will be determined from the conditions that Tp is equal to Tm at r is equal to r, okay, which implies that A1P r is equal to T prime at the surface of the particle and Kp times partial Tp by partial r is equal to Km partial Tm by partial r, which means that A1P is equal to T prime minus 2 V1m by. Okay. Take the derivative of 1 over r square, you get minus 2 by r cubed, evaluated at r is equal to r. Okay. These are two simultaneous equations that can be solved. Okay. These are two simultaneous equations that can be solved for these coefficients A1P and B1m in terms of T prime. The solutions are A1P is equal to 3 T prime by 2 plus K R V is equal to where K R is equal to the ratio of the conductivities of the particles and the matrix. Okay. This is the ratio of conductivities of particle and matrix. This is greater than 1 for a particle that is more conducting and less than 1 if the particle is less conducting. So, with this we have determined the temperature fields in the particle and the matrix. Okay. So, the particle temperature field is equal to 3 T prime P1 of cos theta there is a mistake here, this should be proportional to T prime. Okay. Kindly note that mistake. Both A1P and B1M have to be proportional to T prime because that is the inhomogeneous term in these two simultaneous equations. Okay. So, those are the temperature fields in the particle and the matrix. Okay. What is the flux? Okay. What is the flux in the particle? Okay. The z component of the flux in the particle is equal to minus Kp partial Tp by partial z. Okay. Recall that we were calculating the flux in the direction of the temperature variation. Okay. And recall that this combination r times P1 of cos theta, this combination r times P1 of cos theta is z because cos theta because P1 of cos theta is equal to cos theta itself and r cos theta is z, the vertical direction, because the angle between z and r is cos theta. So, I can write this equivalently as 3 T prime z by 2 plus K r. Is 3 T prime z by 2 plus K r. Okay, so, therefore, this temperature is equal to the heat flux is equal to minus Kp that is the heat flux within the particle, and as you can see that is independent of position. That is independent of position within the particle. So, let me just summarize what we have done so far. Heat conduction in a composite, spherical inclusions of radius r with thermal conductivity Kp in a matrix of thermal conductivity Km. And we wanted to find the relation between the average flux and the applied temperature gradient. The applied temperature gradient is the difference in temperature divided by the length. The Laplace equation is applicable for the temperature in the particle and the matrix. Boundary conditions are that at the particle surface, the temperatures are equal, the fluxes are equal, and far from the particle, the temperature is equal to T prime times Z. Okay, so those are the conditions. This is a problem which is symmetric around the Z axis, where the temperature field at the in the limit as r goes to infinity, the temperature field depends only upon Z, which is r cos theta, and boundary conditions are applied at the surface of the particle at r is equal to capital R, okay, at the surface of the particle where r is equal to capital R. Therefore, the temperature is only a function of r and theta. Okay. And we had solved the Laplace equation in the theta direction in order to get finite results at theta is equal to 0 and theta is equal to pi. We had shown that the eigenvalue in the theta direction has to be n into n plus 1. Okay. And from that we had got the temperature dependence on r and theta as a into r power n plus b by r power n plus 1 p n of cos theta. Okay. So, that was the temperature dependence. Boundary conditions at the surface were homogeneous. They did not introduce any forcing. They just relate the temperature in the particle and matrix at the interface and the flux in the particle and the matrix at the interface. The forcing is in the limit as r goes to infinity, and it is of the form the matrix temperature is equal to T prime times Z, a linear temperature profile far from the particle. And T prime times Z can be expressed as T prime r times P1 of cos theta. Since all the Legendre polynomials are orthogonal, the forcing at r going to infinity contains only one Legendre polynomial P1. The coefficients of all others are identically 0. Okay. And therefore, for all the coefficients for n is not equal to 1, okay, the boundary conditions at infinity, the boundary condition at r is equal to capital R, and the equations are identically satisfied if the coefficients are all 0. Okay. So, therefore, the only non-zero coefficient is for n is equal to 1. Okay. And in that case, the particle temperature is A1 times r plus B1 by r square times P1 of cos theta, n is equal to 1. Similarly, for the matrix, B1 in the particle has to be 0, so that the temperature is finite at the origin at r is equal to 0. A1 in the matrix has to be T prime, so that the temperature is the same as the linear temperature gradient far from the particle. And from the boundary condition at the interface, we have determined what is the coefficients, okay, the temperature field in the particle and the matrix, okay, and the flux in the z direction. Okay. This was for one particle in a composite consisting of a large number of particles dilute, so that the temperature disturbance due to one particle does not affect the temperature field around another particle. So, now we know what is the temperature disturbance and the flux due to one particle. Now, we have to sum this up in order to determine the temperature disturbance and the flux due to all of the particles, and from that we need to evaluate what is the effective thermal conductivity of the composite. This we will continue in the next lecture. I will see you then.